Certainly, we cannot define exponential function on d in a modular way, because d to the power k is not modular operator. I propose the following construction. We consider several modular differential operator. I remind you that dk, by definition, this is d plus 2kg2, and the operator maps the space of modular form of weight k into the space of modular form of weight k plus 2. Now, we start with mk, then we can use dk, we get the space mk plus 2, then we use the modular differential operator dk plus 2, and so on, till the space mk plus 2n. The last operator is dk plus 2n minus 2. The result, the composition of n modular differential operator, we denote by dk, n. Do we have a formula for this operator? This formula certainly is rather complicated, and we don't need it. I would like to calculate this operator a modular form, or it's better to say, I would like to calculate its major term of order n. Let me explain this idea. When we analyze the action of differential operator on the quasi-modular Eisenstein series G2, we found then, I remind you the definition of this operator for D2. D2, this is the modular operator which transforms the space of quasi-modular form generated by G2 in the space of modular form of weight 4. More exactly, D2 in G2 is equal to dG2 plus 2 times G2 times G2. Because in the modular differential operator, we have the operator of multiplication by G2. The result is up to the constant, the Eisenstein series of weight 4. But I don't care on this constant. I would like to rewrite this identity as follows. D in G2 is congruent to minus 2G2 to the square modular M4. And now I would like to make the calculation so we calculate dkn modular some modular forms. And I would like to control only the major term of order n. Now I can formulate the result, the theorem. The major term of this differential operator, dkm, on the nth iteration of the modular differential operator is capital E k n is equal to the sum nu from 0 till n factorial nu factorial n minus nu factorial, the binomial coefficient. Then we have the quotient of two gamma functions, gamma in k plus n over the gamma of nu plus n, and then the product of the quasi-modular Eisenstein series to the power n minus nu, and then the differential operator to the power nu. So this operator transforms the space of modular form of weight k into the space of modular form of weight k plus 2n. Please analyze the formula. In this iteration, we have to calculate a lot of images of this type, and we calculate them using only this congruence. In principle, you can forget about this discussion that this function e is the major term of the differential operator dkm, because now we have to prove that this is a modular differential operator, and we can prove it using the induction proof. Induction by the index n and in this induction I would like to repeat it. Maybe I use another color. We use the only relation, then d on g2 is congruent to minus 2g2 to the square plus g2 times d modular m star. This is the only relation which we use. And using this relation, you can prove, this is elementary calculation, then ekn plus 1 is equal to d, the modular operator of weight k plus 2n, the action of this modular differential operator on the space mk plus 2n, it means on ekn. And then we have to correct this term, but minus 10 over 6, the Eisenstein series of weight 4 in tau, and then ekn minus 1. So you can check this identity by the elementary calculation, because maybe dk plus 2n is equal to d plus 2k plus 2n multiplication by g2. So you have to act by d on all Eisenstein series in our function. So the only identity, I would like to repeat this, only one congruence gives us this identity. And this gives us the theorem. And now, how to simplify this operator? Certainly in our operator, you see the convolution of the differential operator, d, and the powers of the quasi-modular Eisenstein series. So now I would like to define the following formal power series. E, this is analog of the exponent of the differential operator in x, is equal to the sum n greater or equal to 0. I would like, first of all, to divide the operator E, K, N by the numerator. Then we have E, K, N, x to the power n. And certainly, if we divide by the numerator, we can write this formal power series as a product of e to the power 2g 2 times x, and then the next operator, the sum. The rest will be 1 over nu factorial gamma nu plus n. In the numerator, we have the differential operator d nu, the sum for all nu, x to the power nu. So we proved this identity, which I would like to analyze now very carefully. Let me repeat the fact we proved. First of all, we proved the theorem, then the corresponding, the major part of the iteration is the modular operator. Then we write down the formal decomposition of the formal power series of our quasi-exponential function, or it's better to say it's a Bessel function, of the differential operator.